Okay, so let's continue with looking at temporal difference learning. And this lesson we're talking about, we talked about temporal differences before, the basic temporal difference learning, and we had a method called, that we referred to just as TD0, and I gave kind of brief description of why. So we'll go into more now why that is. And we can have modified versions of SARSA and Q-learning that are easier to implement and actually are more powerful, do more than the basic versions we had. So the idea here, basically, to summarize it up front, is to say where the temporal difference was that we're taking the differences in values, and we'll go over what that looked like, the differences in values between what we expect to happen at the current time step and at the following time step, essentially what our value function, our value for our current state and action, and the difference between that and what we actually see and experience from what we expected for one step in the future. So after you take an action and you get some reward, you've learned something, and then you use your model to fill in all the gaps about what happens in the future, and you compare the differences on that, just subtracting out this difference of the reward you actually saw. So like we said, it's kind of measuring the surprise at how different your model is, and you want to improve your model to compensate for that. But we did that just for a single step. And so it's natural to say, well, why can't we learn from many steps and say, well, what about I could use my model, my Q value function. I could say, let's look at what it expected to happen over the next 2 steps, or the next 3 steps, and then actually take 3 steps and look at the rewards I actually obtained over those 3 steps, and then compare that to what I got over those 3 steps as expected from our value function. And so that's a perfectly legitimate thing to do. And so that's what all of this TD lambda temporal difference learning is. So the simple way to think of it is that you're at your current time step, right? So we're going to call this the current time where we are now, right? And you have some value function, right? QSA for that current step. And then after you take your actual step, you're going to get an actual reward, right? And once you take that reward and you end up in the next state, you can now say, well, what would I have expected, right? Because QSA for some other A that we take would give us what we would expect to happen, how much value so the QSA tells us what we think will happen into all of the futures from here, right? If you think about what that means. Whereas our original QSA, which was for this state that we're in, assuming that we've started here in state S and we took action A, right? That's this time step for all of the algorithms. QSA, it's our expected value for following the current policy into the future, right? And that includes the reward we expect to get. After we take that action, we see an actual reward and get an actual next step. Now we're in a position to compare, essentially, the actual R we got plus the Q we'd see in the future states versus this, right? So it's really a battle between these 2 things. And we want to say, if they're not the same, then we want to improve it so that it's closer to the reality, because this R is the only reality we actually have, right? And so the same thing would happen if you had multiple steps, right? And you just say we'd get RT, we'd get RT plus 1, and then you'd want to compare that to Q, whatever, how many ever steps ahead you are, right? The actual differences, right? Now, if you think about in the longer term, when we talked about Monte Carlo methods, that's essentially what a Monte Carlo method is, where we go all the way to the end. Because remember, at the end here, we say we get the reward at RT, which is the final reward we get, and then we go back and we figure out basically how good all of this was, right? So we evaluate our action at this first step, SA, given how good it is here, but always updated by, the value function and the the probability of basically reaching here, right? Because along the way we could have gone through any number of trees, and so Monte Carlo says, well, how likely is it you got to this place? How much was it? And then update all the states along the way based on that. That's kind of the extreme case. Right, so we have our Monte Carlo method. We're basically always combining these rewards into the future, but with that discounting, saying future states aren't as important as current states. So you still mostly want to do well in the next step, but you don't know what it is until you get to the end, right? And we agreed that's kind of not very practical in a lot of cases. So for TD lambda, I've got some nice slide here to compare to. We could say that for TD, we could say that, and now the textbook kind of just has describing it this way, but it's kind of abrupt, so I'll kind of derive that. You could say that the return you're getting at one step ahead is just the reward you got for that time step plus discounting plus your value function, and you use value function to define the rest of that. So that's a bit much to roll into one place, so let's roll that out. If we have the defining how we defined TD 0 before, right, we're going to have our value. What's our Bellman backup update? We're talking about these backups. The value function is just going to be the value function plus this thing we're going to be learning, right? So this alpha, which is our learning rate. So it's the return we actually got at time t, right? And then we want to say we're going to have discounted, because for the next time step we use our model v, and we say, well, what would the value of that next time step be, assuming our model's correct? And then we're going to subtract the value of what our model said about being here, right? Because this is VST, which is, this is what we thought would happen. Here's what actually happened. There's a meme there somewhere. What I thought would happen. Formula. What actually happened. Formula. And it'd be like the most nerdy meme. Somebody do that. What actually happened. I'm going to try to do that if I remember. If we expand this out then, what do we get? So we're going to say, we're going to have 1 minus alpha of VST, right? And then we're going to have our learning rate. Alpha is how much we want to learn about, we're willing to learn from being wrong, isn't it, right? What is alpha? I should have you guys write and explain what alpha and all these things mean. So that's the return, the reward we actually got, and then we have a value. This is not changed. Right? And so now if we say, if we make the assumption now as if alpha eventually is supposed to go towards 1, somebody asked about moving alpha from 0 to 1 or from low to 1, you really could do that. You could say, well, initially I want to have alpha be smaller so that I actually look at my current knowledge and learn, but eventually I want to learn. You could assume you want to learn from your new experiences. So if we expand it that way, then in the end we get this definition of the reward we got for that next step, right? And my t's are off here, so you have to make sure you have your t's correct. The in annotation of t for the value function is a good idea, because you could say this is like the version of that function at time t, and this is the version of it at time t plus 1, right? Using the old copy. If you just overwrite it, then it doesn't matter, but you should know that you're overwriting it. One thing I was going to draw for you guys here that I had last year when I was explaining this stuff is looking at this as a state diagram. And we never really did this, but it's a nice notation. So there's sometimes MDPs are defined in this notation, which are known as influence diagrams, which I like. And so they have shapes that kind of mean all the things that we need them to be here. So we have our state, which is which represents a circle, which represents something that we observe about the system. We're taking action, which are squares. So these are things where you have to decide. So some function has to kind of like figure out what to do here and tell it what the value should be, or a policy. And then you have your utilities, which are represented by diamonds in the influence diagram notation. And so an NDP is just talking about you're in some state, you take some action based on that state, you get a reward, and then depending on how you define the dynamics function, you get to end up in a new state of the world, right? By taking into account these components, right? The reward doesn't influence how the world progresses, hopefully. And then after that happens, you end up in a new state, right? And it all repeats. And you could say that kind of eventually you end up getting I don't know what I meant about having a value function in there. It's not really well defined to call it a value function. That's sufficient. So, but it would keep going on, right? So you'd have the new action, t+1, right? You'd have a new reward, t+1, and so on. And so you can actually define kind of plates with recurrent notations here, and so you have this many steps and actually have it kind of represented as a diagram that way. And so it's a dynamic notation for representing these kinds of really probabilistic models, right? Because there's probabilities here, there's things that you can be estimating, and then you can be defining them in terms of other elements in the system, right? So this is called plate notation when you're doing it this way. Okay, so continuing here, how does this relate then to what I would call the direct method? If we think of the methods back where we were doing value iteration, in the original definition of the Bellman equations, we had V, and what did we set it equal to the reward for that state. So I'm looking at some notes here where I'm copying different versions of it, and actually something's got to match the notation. So what are we using here? We are using RT, so let's stick with that. So the value function for the state t, you get some reward at that time step t. And so you could call that, sometimes you'll see that as R for the state. There's just another way of thinking about it. A little thought bubble here. Remember in value iteration, though, then we'd add the gamma discount factor for future steps. And then we just have st+1 for the next state. Right, and then we have to have the dynamics. So we were calling that P originally, so it's the transition dynamics of ending up in the next state, st+1. And if you start off in the current state and took some action, remember that action is coming from a policy. So let's assume we have a policy that we can take in some given state, st, and then that will give us the action. All right, so that will give us our AT. And then, of course, we have our value function, which tells us what we expect to happen after from state st+1 going forward with the current policy. So compare that to the temporal difference method here, and you can see we're essentially weighting this difference and doing it differently than weighting it by the probability of an outcome. Right, so what's the probability of us getting to this next state? We're looking at the difference between the state at time t and t+1 and our difference in values, whereas in the original version we're weighting that by the probability of ending up in those states and having a distribution over them. So it's kind of more sample efficient because you're picking an actual experienced difference and using that to bootstrap your learning rather than doing an expectation over all states.